In this video, we're going to be looking at using electron configurations and how to create them. Electron configurations are important in understanding how electrons are distributed. So electron configurations show the distribution of electrons within a specific atom or molecule based on atomic orbitals. And it's important to understand the periodic table when it comes to creating electron configurations. The more familiar you are with the periodic table, the easier writing electron configurations will be. So let's look at a periodic table. So in this periodic table, we don't have any of the elements here. We're really just trying to see where each of the orbitals are. So this periodic table is broken up into 4 parts. We have the S, which is indicated in blue, the p orbital, which is indicated in green, the d orbital, which is indicated in yellow, and the f orbital, which is indicated in orange. So what's important to keep in mind here is where each of these orbitals are. So if you were to look at the periodic table with the actual element names, you would be able to recognize that, oh, this orbital or this element might be in the s orbital, or it's in the p or d or f orbital. So understanding where these orbitals are is really important. The other thing that's important to keep in mind is the number of electrons that each orbital can hold. So the s orbital can hold up to 2 electrons, the p orbital can hold up to 6 electrons, the d orbital can hold up to 10 electrons, and the f orbital can hold up to 14 electrons. That is really important when we're trying to write our electron configuration. So really 2 important things to remember from the periodic table when we're making these electron configurations. We need to know where each orbital is on the periodic table, and that's important when we're figuring out what element we're going to be using. And from those orbitals, we need to know how many electrons each orbital can hold. So remember 2, 6, 10, and 14. Those are very important to keep in mind. So let's actually look at writing out these electron configurations. So this is the long way of doing this. I already have the elements and some examples of some elements and their actual electron configurations completely written out. So starting off really simple with hydrogen, for example, being that is the first element on the periodic table. If we looked at the periodic table, we'd recognize that it's in the 1s orbital. And s orbitals, as we know, hold up to 2 electrons. And since it's that first element within that 1s orbital, we know it only has 1 electron. If it were helium, for example, which is the second element in that 1s orbital, it would have up to 2 electrons. So it would be 1s2 rather than 1s1 like hydrogen. So it's pretty simple. You just need to count the electrons based on what orbital it's in. Using that knowledge, let's go on to something a little more complicated, such as nitrogen. Nitrogen is the 7th element on the periodic table. If you look at it, it is in the 2p block. So it's within the p block, it's in the 2p orbital, and we count each electron, or count each element before that. So let's say with nitrogen, we know it's got a full 1s2 shell. That's because it comes after that orbital. It has a full 2s2 shell because it comes after that orbital. So the next orbital is the 2p orbital. Now we know each p orbital has up to 6 electrons, and being that nitrogen is the 3rd element within that orbital, it will have 3 electrons. So if we were to write the full electron configuration for nitrogen, it would be 1s2, 2s2, and 2p3. A little more complicated, but still pretty manageable. Let's look at something a lot longer than that, and that's zinc. Zinc is a transition metal, and it's within the d block. Now, before I get into what it is, it's important to keep in mind that when you work with d orbitals, or you get to the d block, the d orbital, when you're writing the electron configuration, will come before that s and p orbital. And I'll explain that when I get into what it is for zinc. So zinc, like I was doing with nitrogen, we see what is full in terms of the orbitals. So we know the 1s orbital is full, the 2s orbital is full, the 2p orbital is full, the 3s orbital is full, and so is the 3p6 orbital. So all of those each have their full number of electrons, and we're good to go there. So the next thing we have is that's when we start getting into the d orbitals. And like I said before, the d orbital will come before any s or p orbital when you're working with like transition elements. So zinc, since it is the 10th element within that d block, we can say that its electron configuration up to that point is 3d10. So we have everything that is full, including 3d10, and then we also know that the 4s orbital is full as well. So pretty long, but the electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, and 4s2. It's a little long, but we'll get into a shorter way of doing that later. Another way of doing this is bromine, just another example to make it even more complicated by adding a p block into there. We do the exact same thing. We figure out which ones are full, so we get all the way to the 1s, 2s, 2p, 3s, 3p. We know those are full. Then once again, we do 3d first before the 4s, so we know the 3d and the 4s are full, and then we get into the p block. And since bromine is the 5th element of that p block, and we know that the p can hold up to 6, we're going to say that is 4p5. So the full electron configuration for that one is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p5. Pretty long, it's a mouthful, but there's an easier way of doing this. So let's look at the short way of doing this. So hydrogen will actually stay the same because there's nothing else to it. It's just the 1s1 element. It's in the 1s block, 1s orbital. Nothing's going to change for that. But you're going to see when we're working with everything beyond the 1s orbital, you can actually shorten the electron configurations by a lot by saying that we know that everything within or behind that is actually filled, and we can indicate that by using the noble gas that it's closest to. So the noble gas that nitrogen is closest to that is full is helium. So helium, everything from including helium behind it is full. So we can say helium and then 2s2, 2p3. It's a much simpler way of writing it, and we can see that especially for something like zinc and bromine, where zinc, everything from behind argon is full for zinc. So we just say argon, 3d10, 4s2, because those are the orbitals that are like not exactly full. Bromine is the same thing. We also have argon, 3d10, 4s2, 4p5. So really everything from argon and behind that is full, and then we write what is left for bromine. Next, something a little added step is when we're working with ions. And I put this little note here. It's important to note that you remove electrons from s orbitals before removing electrons from d orbitals, and this is true when we're working with ions. So let's say we're working with zinc 2+. We're removing 2 electrons, as indicated by the 2+. So that means we're going to use the shortened way of writing this again. So we write argon first, and then we remove 2 electrons. And in this note, I pointed out that we remove s orbitals before, or remove electrons from s orbitals before d orbitals. And because of that reason, our new electron configuration would be 4s0 3d10, or an easier way of writing it would just be ar 3d10. For something like silver plus, which is just removing 1 electron, we do the exact same thing here. Krypton is the full noble gas that we have in this case. So we would be removing 1 electron from the s orbital. So it would be 4d10, or krypton 4d10, 5s1. So pretty simple, just it's important to keep in mind that we're removing electrons from s orbitals before d orbitals. So to summarize, it's important that we locate the desired element on the periodic table. From there, we can determine which orbital the element lies within. And from that point, we can begin writing configurations based on the order of the orbitals. And also, if we know that the element is an ion, we can add or remove electrons from the correct orbitals. Like I said, remove electrons from s orbitals before d orbitals. But that pretty much summarizes how to create an electron configuration.